Look up, gaze into the velvet darkness of the night sky, a canvas pricked with the diamond dust of 1 billion distant suns. For all of recorded history, this view has been our mirror, reflecting our questions, our fears, our aspirations. It is the ultimate context for the human story. We have told ourselves a comforting tale about this place, a story of uniformity, of a grand cosmic democracy. The narrative insists that our location, our galactic home, is unremarkable, a typical address in a universe that, on the largest scales, looks the same from every vantage point. This is the principle of mediocrity, the bedrock of modern cosmology. It's a neat, orderly, and philosophically satisfying picture. But what if this story, the one we've been told for a century, is built upon a profound misunderstanding? What if our cosmic address is not typical at all? What if the very fabric of our reality, the space for billions of light years around us, is an anomaly, a place fundamentally different from the great beyond? Imagine discovering that the city you've always known as the world is actually a secluded village in a vast, uncharted desert. This is the story of a monumental cosmic secret. A revelation that we are adrift inside a colossal hole in the universe, and until recently, nobody even knew to tell us. Our quest to understand this secret begins not in the cold void of space, but in the warm glow of human curiosity. Centuries ago, for millennia, the universe was a cozy, intimate affair, a celestial sphere, perhaps, with the Earth held firmly at its center. The stars were fixed points of light, divine decorations on a celestial ceiling. This was a universe made for us, a stage for the human drama. The revolution began quietly, with meticulous observations and courageous mathematics. Copernicus, Kepler, and Galileo dismantled this geocentric comfort, displacing humanity from the heart of creation. With the invention of the telescope, our cosmic horizons began to recede, revealing a universe far larger and more complex than we had ever conceived. Our sun became just another star, and our solar system a minor outpost. The next great leap into the cosmic ocean occurred in the 1920s, atop Mount Wilson in California, where a man named Edwin Hubble was systematically charting the faint, hazy patches of light known as nebulae. The prevailing wisdom of the time held that these were nascent solar systems, swirling clouds of gas within our own Milky Way galaxy. But Hubble, using the colossal 100-inch Hooker telescope, found something that would shatter our perception of reality. Within the Andromeda Nebula, he identified a specific type of star, a Cepheid variable, a pulsating star whose rhythm is intrinsically linked to its true brightness. It was a standard candle, a cosmic yardstick. By comparing the star's apparent dimness to its known intrinsic luminosity, Hubble could calculate its distance. The number he found was staggering. Andromeda was not a nearby cloud. It was nearly 1 million light-years away, an island universe of hundreds of billions of stars, entirely separate from our own. The universe had not just expanded, it had exploded in our minds. Our Milky Way was but one of countless galaxies scattered through the depths of space, but Hubble's most profound discovery was yet to come. As he measured the distances to more and more of these galactic islands, he noticed a peculiar, universal pattern in their light. The light from almost every galaxy was stretched, shifted toward the red end of the spectrum. This was the Doppler effect, the same phenomenon that makes an ambulance siren sound lower in pitch as it speeds away from you. The galaxies were not stationary, they were all rushing away from us. And more astonishingly, the farther away a galaxy was, the faster it receded. The conclusion was inescapable, world-altering. The very fabric of space-time itself was expanding. The universe was not a static stage, but a dynamic, growing entity. A common analogy is that of a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be receding, and the more distant ones move away faster. There is no center to the expansion. It is happening everywhere at once. This discovery gave birth to the Big Bang Theory, and established a new cosmic dogma, the cosmological principle. This principle states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means it has a uniform composition and density. No matter where you are, the average amount of stuff around you is the same. Isotropic means it looks the same in every direction. There are no preferred axes, no special alignments in the cosmos. Our raisin, in other words, is no different from any other raisin. Our view of the expanding universe is the same view anyone, anywhere would have. This principle was not just an elegant theory. It became the fundamental assumption, the starting point for nearly all of our models of the universe. As our technology advanced, we began to map this universe in 3 dimensions. Vast surveys painstakingly measured the positions and redshifts of millions of galaxies, painting a portrait of the cosmos on an unimaginable scale. What emerged from these maps was not a uniform, featureless distribution of matter. Instead, it was something far more intricate and breathtakingly beautiful. The universe, on the largest scales, is structured like a sponge or a neural network. Galaxies are not scattered randomly like dust. They are drawn together by gravity into unimaginably long, glittering filaments and dense, crowded intersections. These are the superclusters, the great metropolitan hubs of the cosmos, teeming with thousands of galaxies, each a city of billions of stars. These filaments connect to one another, forming the walls of a colossal structure that astronomers have poetically named the cosmic web. It is the largest known structure in existence, a luminous tapestry of matter, woven across hundreds of millions of light years, a glowing skeleton of creation. It is a picture of sublime complexity, a universe of breathtaking architecture. But this grand tapestry also reveals a profound emptiness. For every glittering filament and every dense supercluster, there are vast, dark, and astonishingly empty regions that separate them. These are the cosmic voids. They are the great deserts of the universe, immense bubbles of near-nothingness. They are not truly empty. They still contain a sparse scattering of galaxies, lonely drifters in an ocean of quiet desolation. But their density is a fraction of the cosmic average. While the filaments are the bustling highways of the universe, the voids are the silent, forgotten backwaters. For decades, we saw these voids as mere gaps in the cosmic web, the spaces between the interesting parts. We mapped them, catalogued them, and assumed we lived far from them, safely nestled within a typical, unremarkable strand of the cosmic web. That assumption, it turns out, may have been the greatest mistake in modern cosmology. The first hint that something was profoundly wrong with our standard story came from a persistent and deeply troubling disagreement, a mystery that cosmologists now call the Hubble Tension. It is a conflict born from our 2 most powerful methods of observing the universe, a schism between the cosmos in its infancy and the cosmos as it is today. The problem revolves around a single number, the Hubble constant, a figure that represents the current expansion rate of the universe. Measuring this number has been a holy grail of astronomy for a century. The first method is to measure it directly, here and now. This is the local measurement, a technique that builds upon Edwin Hubble's original work. It's called the cosmic distance ladder, and it requires astronomers to meticulously measure distances rung by rung out into the universe. The first rung relies on parallax, a form of cosmic triangulation for nearby stars. The next rung uses those Cepheid variable stars, the pulsating beacons, first used by Hubble, whose rhythm betrays their true brilliance. By calibrating Cepheids in our own galaxy, we can then find them in nearby galaxies and determine their distances with incredible precision. The final rung of the ladder uses a much brighter, much rarer event, a Type Ia supernova. These are the thermonuclear explosions of white dwarf stars, and they are astonishingly consistent. Each one detonates with nearly the same intrinsic brightness, making them the ultimate standard candle, visible across billions of light years. By finding galaxies that host both Cepheids and these supernovae, we can calibrate the brightness of the explosions. Then, we can look for these cataclysms in the far-flung corners of the cosmos. to measure the expansion rate deep into cosmic history. Led by Nobel laureate Adam Rees, teams have spent decades refining this method, using the Hubble Space Telescope and other observatories to build a robust, high-precision measurement of the local expansion rate. The number they have settled on is approximately 73 kilometers per second per megaparsec. This means that for every 3.26 million light-years you travel away from us, the universe is expanding 73 kilometers per second faster. This number seems solid, a triumph of observational astronomy. But there is another way to determine the expansion rate, a way that does not look at the universe today, but at its very beginning. This second method involves studying the oldest light in existence, the faint afterglow of the Big Bang itself. This is the cosmic microwave background, or CMB. It is a faint, pervasive hum of radiation that fills all of space, a snapshot of the universe, when it was a mere 380,000 years old. Back then, the cosmos was a hot, dense, opaque fog of plasma. As it expanded and cooled, atoms formed, and the universe suddenly became transparent. The light that was present at that moment was finally set free, and it has been traveling across the cosmos ever since, its wavelength stretched by cosmic expansion from brilliant light into cool microwaves. Satellites like WMAP, and more recently, the European Space Agency's Planck Observatory, have mapped this ancient light with extraordinary sensitivity. The CMB is not perfectly uniform. It is dappled with minuscule temperature fluctuations, tiny ripples that represent the seeds of all future structures. These ripples encode a wealth of information about the early universe. They tell us its age, its composition, the precise amounts of dark matter, dark energy, and ordinary matter, and crucially, they contain a prediction. Contained within this baby picture of the universe is a complete cosmological model known as lambda CDM. This model, our standard model of cosmology, is incredibly successful. And when you feed all the precise data from the Planck satellite into this model, you can calculate what the expansion rate of the universe times should times be today. It allows you to wind the cosmic clock forward 13.8 billion years. And this is where the crisis begins. The number predicted by the Planck data and our standard model of cosmology is not 73. It is approximately 67 kilometers per second per megaparsec. These two numbers do not agree. They are not even close. The error bars on both measurements are now so small that there is no overlap. The chance that this discrepancy is a statistical fluke is less than 1 in a million. This is the Hubble tension. It's a tale of two universes. The early universe, observed through the CMB, is telling us one story about how it should be expanding today. The local, modern universe, observed through supernovae, is screaming a different story. Something is wrong. Either our measurements of the local universe are flawed, our understanding of the early universe is mistaken, or the cosmological model that connects the two is incomplete. For years, cosmologists have searched for errors in the measurements, recalibrating their yardsticks, reanalyzing their data, but the tension remains. It has become the single biggest crisis in modern cosmology, and it is not the only strange clue that our cosmic neighborhood is unusual. Another anomaly lies imprinted on that same baby picture of the universe. When astronomers studied the Planck map of the CMB, they found something that, by all rights, should not be there. In the direction of the constellation Eridanus, there is a patch of the sky that is anomalously, inexplicably large and cold. This isn't just a minor fluctuation, it is the most significant deviation from statistical randomness on the entire map. Known as the CMB cold spot, it is a chilling fingerprint of something immense. Initial, more exotic theories suggested it could be a bruise from a collision with another universe, a cosmic texture, or a flaw in the fabric of space-time. But a far more mundane, yet no less profound, explanation has since gained traction. The cold spot might be an illusion, a trick of cosmic geography. It could be caused by the light from the CMB having to travel through an exceptionally large and empty region of space on its way to us. This is a phenomenon known as the integrated Sachs-Wolf effect. Imagine a photon of light as a marble rolling across a rubber sheet. If the marble rolls into a dip representing the gravity well of a galaxy cluster, it gains energy and speeds up. As it climbs back out, it loses that same amount of energy, emerging with its original momentum. But if the universe is expanding and dominated by dark energy, the gravity well becomes shallower while the photon is inside. So, when the photon climbs out, it doesn't have to work as hard. It leaves with a net gain of energy, appearing slightly hotter or blue-shifted. Conversely, if a photon travels through a vast void, a region with less mass and thus a sort of anti-well or hill in space-time, the opposite happens. As the photon enters the void, it loses energy, climbing the gravitational hill. While it's inside, the expansion of the universe stretches and flattens the hill. So when the photon rolls back down the other side, it doesn't regain all the energy it lost. It emerges from the void with a net energy deficit, appearing slightly colder or redshifted. The CMB cold spot could therefore be the ghostly signature of a truly colossal void, a billion light-year-wide chasm in the universe, sitting directly in our line of sight. Surveys of galaxies in that direction have indeed found such a structure, the Eridanus supervoid. But even this gargantuan emptiness is not quite large enough to fully account for the temperature of the cold spot. Unless that supervoid is merely a part of something much, much bigger. Something that doesn't just lie in our line of sight, but that completely surrounds us. This brings us to the precipice of a radical and transformative idea. An idea that connects the Hubble tension and the cold spot, tying these disparate clues into a single, cohesive narrative. The hypothesis is this: the Milky Way, our entire local group of galaxies, and indeed our entire Laniakea supercluster, are all located inside one of the universe's great cosmic voids. We are living in a cosmic hole. This proposed structure is known as the KBC Void, named for the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie who first proposed it. It is a bubble of underdensity, of almost unimaginable proportions. Its estimated diameter is a staggering 2 billion light-years. It is one of the largest structures ever conceived. To call it a hole is perhaps misleading. It is not a perfect vacuum. It is a region of space that is simply 20 to 50% less dense than the average of the universe as a whole. It is a cosmic basin, a vast, shallow valley in the topography of the cosmos. Imagine the cosmic web is a magnificent, sprawling forest. We have always assumed we lived in a typical grove, surrounded by trees. This new idea suggests we actually live in a gigantic clearing in that forest, a meadow so vast we couldn't see the tree line for generations. How could such a monumental structure solve our greatest cosmic puzzles? Let's start with the Hubble tension. The solution is a matter of perspective, a consequence of gravity and location. If we are inside a colossal, underdense bubble, then the regions outside the bubble, the dense walls of the void, contain significantly more mass. This means the matter outside our bubble exerts a stronger gravitational pull on everything inside the bubble than the sparse matter within it does. This creates a powerful net outward force. It is like being in the center of a giant, spherical trampoline, where heavy weights have been placed all around the distant rim. The fabric of spacetime in our local area is being stretched outwards by the gravitational attraction of the denser universe beyond our void. This local outflow, this gravitational tide pulling us toward the void walls, is a motion that is entirely separate from the global expansion of the universe. It is a local current in the great cosmic river. So when we measure the recession of galaxies from our vantage point, we are measuring two things at once. We see the uniform, global expansion of space-time described by the Big Bang, the 67 value predicted by the CMB. But on top of that, we are also measuring this additional, local, outward flow. The two effects combine. The local flow effectively inflates our measurement of the global expansion. It makes it look times like the universe is expanding faster from our perspective than it actually is on average. The 73 value is not the true Hubble constant. It is a locally biased measurement, contaminated by the fact that we live in a cosmic hole. The Hubble tension, in this scenario, is not a tension at all. It is a direct consequence of our atypical address in the cosmos. The early universe measurement from the CMB gives us the true global average expansion rate. Our local measurement using supernovae gives us a higher, provincially inflated value. Both measurements can be correct. It's our assumption, the cosmological principle, that was wrong. We assumed our view was typical, but it is not. We are being pushed and pulled by local structures in a way that creates a cosmic mirage. This single, elegant idea also naturally enfolds the other great anomaly, the CMB cold spot. If we are in a giant void, then it is not surprising to find other large voids, like the Eridanus supervoid, nearby. Our location within this vast basin could mean that the path of the CMB photons from the cold spot's direction has been traveling through underdense regions for longer, losing more energy, and thus appearing even colder than a single void could explain. Our local environment becomes the missing piece of the puzzle. The implications of this hypothesis are nothing short of revolutionary. It represents a direct challenge to the Copernican and cosmological principles, the very idea that we are not in a special place. The Copernican revolution taught us we are not at the center of the solar system. Hubble taught us we are not in the central galaxy of the universe. The cosmological principle was the final step, asserting that our location has no significance whatsoever, but living inside one of the universe's largest voids times is times special. It makes our position cosmically relevant again, not in a privileged, central way, but in a specific, anomalous way. We are back on the cosmic map, not as the capital, but as a strange and remote province. This shift in perspective forces us to reevaluate everything we think we know. Consider dark energy. Its discovery, the observation that the universe's expansion is accelerating, was based on those same type Ia supernovae. Astronomers noticed that distant supernovae were dimmer than they should be, in a universe expanding at a constant rate, implying they were farther away than expected. This led to the conclusion that the expansion had sped up over time, driven by a mysterious repulsive force called dark energy. But if our local measurements have been contaminated by our presence in a void, it could alter our calculations of this acceleration. The apparent speed-up might be, at least in part, another illusion. Perhaps we don't need as much mysterious dark energy as we thought. The behavior of the universe could be explained more by its structure, by the hills and valleys of the cosmic web, than by an enigmatic new force. The philosophical and even existential questions are profound. What does it mean for life to have emerged in a cosmic backwater? Is it a coincidence? Or is there a deeper connection? Perhaps voids are, counterintuitively, more hospitable to the development of complex life over billions of years. The dense filaments of the cosmic web are violent places. Galaxies are constantly colliding and merging, triggering massive bursts of star formation and bathing their environments in lethal radiation from supernovae and active galactic nuclei. A quiet, underdense void might be a safer harbor, a more stable environment where a solar system can evolve in relative peace for eons, undisturbed by cosmic cataclysms, providing the long, uninterrupted quiet necessary for biology to perform its slow, intricate work. Perhaps we are not just in a void, but times from times a void. Our existence could be a testament to the virtues of cosmic solitude. Of course, such an extraordinary claim requires extraordinary evidence. The idea that we live in a cosmic hole is still a hypothesis, and it faces skepticism. Many cosmologists believe the Hubble tension points not to a flaw in our assumptions about location, but to a flaw in our understanding of physics. Perhaps there is some new particle, some unknown interaction in the early universe that has been overlooked in our standard lambda CDM model. This new physics could have altered the expansion rate in the universe's youth, reconciling the two measurements without having to sacrifice the cosmological principle. The debate rages on, a vibrant and essential process at the heart of science. The final verdict will come from the next generation of cosmic cartographers. observatories like the Vera C, Rubin Observatory in Chile, and space telescopes like the European Space Agency's Euclid mission are designed to create the largest, deepest 3D maps of the universe ever attempted. They will chart the positions of billions of galaxies, painting a definitive picture of the cosmic web and its voids. These surveys will either confirm the existence and scale of the KBC Void, showing that we are indeed in a vast underdensity, or they will show that our cosmic neighborhood is, in fact, average, forcing us to look for new physics to solve the Hubble tension. The James Webb Space Telescope is also playing a crucial role, refining our measurements of the cosmic distance ladder with unprecedented accuracy, ensuring that no subtle error has led us astray. We stand at a pivotal moment in our understanding of the cosmos. The comfortable story we told ourselves for a century has begun to unravel. The clues are scattered before us. A cosmic expansion that refuses to be pinned down, a cold spectre haunting the dawn of time, and the tantalizing possibility that our entire world is an anomaly. The journey to this point has taken us from a small, Earth-centered stage to an expanding universe of infinite complexity. And now it has led us to question the very ground beneath our cosmic feet. Look up at the night sky one more time. The light from those distant stars and galaxies has travelled for eons across the vast, structured ocean of space-time. Its journey has been shaped by the invisible gravity of dark matter, stretched by the relentless expansion of the universe, and perhaps deflected and drained by the immense, silent voids that dominate the cosmos. We are not just looking out at the universe, we are looking through it, through its history, its structure, its secrets. The story that nobody told us is the one we are only now learning to read in that ancient light. It is a story that suggests we are children of the emptiness, inhabitants of a great cosmic clearing, and if this is true, it does not diminish our place in the universe, it makes it all the more remarkable. It means our search for understanding has, by a strange quirk of cosmic fate, begun from one of the quietest, most unique places in all of existence. And from this serene vantage point, we continue our endless, humbling quest to comprehend it all. What happens when a star, a billion-year-old furnace of light and life, makes a fatal mistake? What unfolds when its majestic, aeons-long pilgrimage through the void brings it onto a collision course, not with another star, but with the most extreme object permitted by the laws of physics? You are about to witness this final, terrifying encounter. This is not a simulation of a distant possibility. This is a forensic reconstruction of a cosmic execution, a spectacle of such sublime violence that it tears a hole in the silent darkness and screams its existence across millions of light-years of empty space. The star begins its final journey in blissful ignorance, a familiar sphere of incandescent gas tracing its loyal orbit around the heart of its home galaxy. For countless millennia it has swung wide, a safe and stable courtier, to a distant unseen monarch. But something has changed. A gravitational nudge from a passing neighbour, a subtle perturbation in its ancient dance, has altered its trajectory ever so slightly. It is a minuscule deviation, a cosmic rounding error, but it has sealed the star's fate, placing it on a new, parabolic path, a path of no return. As it accelerates, plunging toward the galactic core, the universe around it seems to hold its breath. The familiar constellations of its sky warp and distort the light from distant galaxies, bending as it crosses the increasingly steep gravitational terrain. You can almost feel the rising tension, the silent, inexorable pull of a predator that does not need to hunt. It simply waits. The architect of this impending doom is a supermassive black hole, a silent sovereign of the galactic center, millions or even billions of times the mass of our own sun compressed into a volume smaller than our solar system. It is gravity's ultimate expression, a point of infinite density so profound that it has torn a hole in the very fabric of space-time. Its presence is felt, not seen, a sphere of perfect blackness, an event horizon from which nothing, not even light, can escape. To the approaching star, this region is still a distant dark secret. The first sign of trouble is not a feeling of being pulled, but of being stretched. This is the insidious, brutal physics of the tide. Here on Earth, the moon's gravity gently tugs on our oceans, creating a bulge on the near and far sides of our planet. It's a subtle, life-giving rhythm. But in the shadow of a supermassive black hole, this same tidal force is transformed into a weapon of cosmic demolition. As the star crosses a critical threshold, the Roche limit, the gravitational pull on its nearest side, becomes exponentially stronger than the pull on its far side. This differential is the celestial equivalent of being placed on a rack. The star, a body held together by its own immense gravity, suddenly finds an external force that overpowers its own internal cohesion. The duel is impossibly brief and utterly one-sided. The star begins to elongate, its perfect spherical shape distorted into a grotesque teardrop. Its outer layers of hydrogen and helium, once contained in a delicate hydrostatic equilibrium, are stripped away like gossamer. They form magnificent glowing tendrils, a river of plasma now flowing not into the star's core but away from it, drawn toward the gaping maw of the black hole. This is the moment of its unravelling. The star is not swallowed whole, it is meticulously and violently disassembled atom by atom. What was once a self-contained nuclear furnace becomes a hyper-extended streamer of stellar material, a luminous filament of gas thousands of times longer than its original diameter. One end of this stream plunges directly past the event horizon, a final silent offering to the abyss lost to our universe forever. Its information, its matter, its very existence is erased from view. But the other half of the star, a vast and traumatized remnant, suffers a different fate. Having been whipped around the black hole with ferocious velocity, this material is flung back out into space. It forms a swirling, chaotic accretion disk, a maelstrom of superheated gas glowing with the fury of its own destruction. The friction within this disk as stellar matter grinds against itself, at nearly the speed of light, ignites a blaze of radiation so powerful it can briefly outshine the entire host galaxy. This is the event's death cry, a flare of pure energy broadcasting the star's demise across the electromagnetic spectrum. It is a luminous tombstone, a final fleeting monument to a life annihilated. We call this cataclysm a tidal disruption event. For generations, these cosmic demolitions were little more than ghosts in our equations, a dramatic but purely theoretical consequence of Einstein's relativity. We knew they should happen. The mathematics was undeniable. The universe with its countless galaxies, each harbouring a monstrous black hole at its centre, and each filled with billions of wandering stars, had to be a stage for such tragedies. Statistically, in any given galaxy like our own Milky Way, a star should stray too close to its central black hole once every 10,000 to 100,000 years. A cosmic rarity to be sure, but across the observable universe with its trillions of galaxies, it meant that somewhere at any given moment a star was meeting its end in this spectacular fashion. Yet for all our certainty, they remained elusive, unseen. They were spectres haunting the dark corners of the cosmos, their violent light flashes too faint, too brief, or too distant for our telescopes to capture with any clarity. We were like detectives with a perfect description of a crime, but with no crime scene, no evidence, no smoking gun. The universe was playing a grand game of hide and seek, and these events were its most masterful players. But that has all changed. We have entered a new era of cosmic forensics. A new generation of automated wide-field sky surveys now scan the heavens night after night, their digital eyes tireless and vigilant. They are not looking for one specific object, but for anything that changes. They are designed to catch the universe in the act. These silent robotic sentinels meticulously chart the sky, comparing tonight's image with last night's searching for the telltale flicker of a transient, a new pinprick of light, where yesterday there was only darkness. When one of these surveys gets a hit, an alert flashes across the globe, and within minutes the world's most powerful telescopes on the ground and in orbit can pivot and stare. They become a global multi-wavelength detective agency, examining the fresh cosmic crime scene in X-rays and ultraviolet, in visible light and in radio waves. And through their collective gaze, the ghosts have begun to materialize. We are now finding tidal disruption events not by chance, but by design. We are seeing them unfold, sometimes catching the first glimpse of light just days after the star's initial shredding. What was once a theoretical curiosity has become one of the most exciting and revelatory new windows into the universe's most extreme environments. The light from a dying star is more than just a tragic spectacle. It is a message. It is a physical probe delivered by nature itself into a region we could never hope to visit. The flare from a tidal disruption event acts as a temporary lamp in the darkest room in the universe, illuminating the immediate vicinity of a supermassive black hole in unprecedented detail. As we watch the stellar debris swirl into an accretion disk, as we analyze the spectral signatures of the superheated elements, and as we measure the fading of this cosmic ember over months and years, we are performing a celestial autopsy. But the body on the table is not just the star. We are dissecting the very nature of the abyss that destroyed it. We are tracing the contours of space-time itself. These events are allowing us to ask and begin to answer some of the most profound questions in astrophysics. How do these supermassive black holes grow to such astonishing sizes? Do they feed in a steady trickle or in these rare gluttonous bursts? The debris from the disrupted star carries with it a memory of its journey, and its final incandescent swirl can betray the secrets of the black hole's own properties. The precise shape and evolution of the flare, for instance, can tell us whether the black hole is spinning or stationary. A spinning black hole, a gravitational gyroscope twisting space-time around it, will process the infalling stellar debris differently than a static one, creating a unique light signature that we can now decode. We are for the first time directly measuring the spin of monsters that are millions of light years away using the light of their last meal. It is a technique of staggering ingenuity, using a star as a tool to probe the fundamental nature of a singularity. Furthermore, the journey of this light to our telescopes is itself a source of information. The X-rays emitted from the inner edge of the new accretion disk, where matter is at its hottest and fastest, must climb out of an immense gravity well. Their path is bent, their energy is warped by the relativistic effects predicted by Einstein a century ago. By studying these distortions, we are testing the theory of general relativity in an environment more extreme than any we could ever replicate on Earth. We are watching its predictions play out in real time on a stage where gravity is not a gentle force but the undisputed tyrant of reality. Each new tidal disruption event we discover becomes a new laboratory, a fresh experiment run for us by the cosmos itself. Each one is a unique puzzle, a new set of clues about the black hole's mass, its diet, its environment, and the very structure of the galaxy it commands. This is the central thesis of our journey together. We stand at a unique moment in the history of astronomy. These cataclysms, these stellar deaths of unimaginable violence, are no longer theoretical. They are observable facts. They have been transformed from a footnote in a textbook into a primary tool for exploration. They represent a new frontier in our understanding, a way to shine a light on the hidden architecture of the cosmos. For too long, the hearts of galaxies have been realms of darkness and mystery, their central engines shrouded from our view. But now the universe is providing its own beacons. The final brilliant screams of dying stars are piercing that veil, allowing us to chart the gravitational tides that shape galaxies, to witness the feeding habits of giants, and to explore the twisted, warped reality at the edge of infinity. The story of tidal disruption events is not just a story of destruction, it is a story of revelation. It is the story of how a star's death can give birth to our profound, new understanding of the universe and our place within it. And as we continue to watch the skies, we know that somewhere out there right now, another unsuspecting star is beginning its final fateful plunge, ready to offer up its life and its light to unlock the deepest secrets of the dark. What if the most profound act of creation in the universe and the most terrifying act of destruction are born from the very same force we build our understanding of the cosmos on gravity? It is the gentle hand that holds our planet in orbit, the architect of galaxies, the midwife to stars. But deep in the heart of that elegant mathematics, hidden within Einstein's pristine equations, a monster was stirring. A prediction so bizarre, so violent, that for decades even its creators refused to believe it. They saw a tipping point, a place where gravity, the familiar force of cosmic order, would betray its nature and become an agent of absolute chaos, a force not of cohesion, but of utter annihilation, They had conceived of the black hole not as an object, but as a region of space-time itself warped to an impossible extreme, a wound in the fabric of reality. And at the heart of this wound lay the singularity, a point of infinite density, where all our known laws of physics simply break down, surrendering to the unknowable. Surrounding this mystery is a border, an intangible frontier from which nothing, not even light, can ever return. We call it the event horizon. It is not a physical surface you could touch. It is a philosophical precipice, a one-way door in the universe. Crossing it is not a journey through space, but a journey into the inexorable flow of time itself, a current that pulls you only one way towards the end. For most of the 20th century, these cosmic nightmares were confined to the chalkboards of theoretical physicists. They were mathematical curiosities, the logical but seemingly absurd conclusion of a beautiful theory. Where could such gravitational monstrosities possibly exist? The answer, when it began to emerge, was more shocking than anyone had dared to imagine. Not wandering the lonely voids between the stars, but in the most crowded, most luminous, most vital places of all. They were lurking at the very heart of the great cosmic cities, the sprawling, majestic galaxies that adorn the night sky. Every one of them, it seemed, including our own Milky Way, was built around a secret central engine of immense power, a supermassive black hole. These are not the remnants of a single collapsed star. They are behemoths of a different order altogether, weighing millions, even billions of times the mass of our Sun. They are the unseen anchors of galactic structure, the quiet gravitational tyrants around which hundreds of billions of stars perform their silent celestial ballet. And this presented astronomers with a profound paradox. How do you prove the existence of an object that is by its very definition perfectly black, utterly invisible, and located in the most densely packed, light-drenched region of a galaxy, trillions of miles away? You cannot see the predator itself, so you must look for the signs of its passing. You must become a detective searching for its influence on the world around it. Imagine trying to find a perfectly clear glass sphere submerged in the middle of a vast dark ocean. You would not see the sphere itself. Instead, you would watch how the currents of water bend around it. You would observe how light from a distant source is distorted as it passes by. This is precisely how we first found them. Astronomers turned their most powerful telescopes towards the core of our own Milky Way, towards a point in the constellation of Sagittarius, known as Sagittarius A star. What they found there over decades of painstaking observation was breathtaking. They saw a small cluster of stars whipping around a central point at absolutely astonishing speeds. One of these stars, designated S2, completes an orbit in just 16 years, a mere cosmic heartbeat. At its closest approach to the galactic centre, it travels at over 7,000 kilometers per second, nearly 3% of the speed of light. It accelerates and decelerates with a ferocity that defies any explanation other than the presence of an unimaginable gravitational source. And the most critical detail of all, at the focus of these frantic slingshot orbits there was nothing. No giant star, no dense cluster, just empty blackness. The stars were dancing around an invisible partner, a partner whose mass could be calculated from their orbits. The numbers were staggering. The object at the centre of our galaxy, this silent, unseen choreographer, must contain the mass of 4 million suns, all squeezed into a space smaller than the orbit of Mercury. The monster from the equations was real, and it was in our own cosmic backyard. This discovery was replicated across the universe. Galaxy after galaxy revealed the same signature, a central hub of stars and gas moving with such violence that only a supermassive black hole could be holding them captive. Yet for all their power, they are surprisingly quiet neighbours. Most of the time, they are dormant, quiescent. They are like cosmic volcanoes that have long since slumbered, having already consumed all the gas and dust in their immediate vicinity. The feast is over. The galactic core is swept clean, leaving the central beast in a state of starvation. For eons, it can sit there, a silent gravitational heart, its presence felt but its fury contained. It is a sleeping dragon at the centre of a kingdom that has forgotten the meaning of fire. But what if something were to wake the dragon? What if a fresh meal and unsuspecting victim were to stray from its safe, predictable path in the outer galaxy and find itself on a collision course with this slumbering maw? This was the next great theoretical question. Long before we ever saw one physicist like John Wheeler and Martin Rees began to ponder this very scenario. They asked a simple yet terrifying question. What happens when a star meets a supermassive black hole? Our star, the Sun, is a magnificent engine of stability. For billions of years, it has existed in a state of perfect equilibrium, a delicate balance between two opposing forces. The inward crush of its own immense gravity, desperately trying to collapse it into a single point, is perfectly counteracted by the outward pressure of the thermonuclear furnace raging in its core. It is a contained explosion, a self-regulating gravitational gyroscope, and this balance is what allows life to flourish on Earth. The star is held together by its own self-gravity, a force that binds it into a near-perfect sphere. But that binding force, as powerful as it is finite. It can be overcome. To understand how, we must first understand the nature of tides. Here on Earth, we think of tides as the gentle rise and fall of the ocean, a phenomenon caused by the moon's gravitational pull. But the truth is more subtle and far more violent. The moon does not pull on the Earth uniformly. It pulls more strongly on the side of the Earth facing it, and less strongly on the side facing away. This difference in pull, this gravitational gradient, is what stretches our planet. The solid rock of the Earth deforms by mere inches, but the liquid oceans are free to bulge, creating the high tides we see. Now take that principle and amplify it by a factor of billions. Replace our moon with a supermassive black hole. Replace the Earth with a star. As an unlucky star begins its final fatal plunge towards the galactic centre, it enters a zone of extreme danger. The gravitational pull of the black hole becomes unimaginably intense. But more importantly, the difference. In that pull across the star's own diameter becomes catastrophic. The edge of the star closer to the black hole is yanked forward with a force exponentially greater than the force on the star's far side. The star is no longer being pulled as a single object. It is being stretched. This is the domain of differential gravity, a force that does not seek to capture but to tear apart. The star's own gravity, the force that has held it together for perhaps 10 billion years, is suddenly locked in a losing battle against the tidal forces of a cosmic monster. There is a theoretical boundary around every massive object, a point of no return for anything held together by its own gravity. It is called the Roche limit. For a satellite orbiting a planet or a star orbiting a black hole, crossing this line is a death sentence. Inside the Roche limit, the external tidal forces overwhelm the internal gravitational binding energy of the object. The celestial tug-of-war reaches its brutal conclusion. The star loses. The theoretical models predicted a process of exquisite horror. The star, once a majestic glowing sphere, would begin to deform. It would be pulled into an elongated egg-like shape, a teardrop of plasma aimed at the heart of the abyss. As it gets closer, the stretching becomes more and more extreme. The internal pressures and temperatures would skyrocket, but not in the controlled, stable way of normal fusion. This is a chaotic mechanical shredding. The very fabric of the star is unravelled. Imagine pulling on a ball of dough. At first it stretches and resists, but as you keep pulling it thins in the middle, becoming longer and more fragile until finally it snaps. This is what physicists predicted would happen to the star, a process they grimly but accurately dubbed spaghettification. The star ceases to be a star. It is drawn out into a vast incandescent filament of its own matter, a luminous noodle of superheated gas hundreds of millions of kilometers long. But for this spectacular demise to occur, the conditions have to be just right. The encounter must be a cosmic near miss, a grazing blow. If the star plunged directly towards the event horizon, it would simply be swallowed whole, its light extinguished in an instant, leaving behind no trace of its passing. A silent anticlimactic disappearance. Too far away and the star would be deflected, slingshotted into a new orbit, shaken but intact. The magic, the violence, the observable fireworks all happen in that delicate sweet spot. A trajectory that brings the star close enough to be torn apart, but not so close that it is swallowed, before the drama can unfold. The star must pass inside the black hole's tidal radius, its Roche limit, while remaining outside the event horizon itself. For smaller black holes, the kind formed from a single stellar collapse, this is impossible. Their tidal radius is inside their event horizon. A star would be swallowed before it could be spaghettified. Only a supermassive black hole with its relatively lower density and an event horizon far from its centre of gravity provides the vast stage needed for this drama to play out. The sheer scale of the central beast is what allows for the slow, observable destruction of its victim. The theoretical stage was now set. The mathematicians and physicists had laid out the script for a celestial crime of unimaginable proportions. They had identified the culprit, a dormant supermassive black hole. They had chosen the victim, a common unassuming star, and they had described the murder weapon, the brutal differential force of gravity itself. They had even sketched out the gory details of the act, the transformation of a sphere of light into a thin streamer of plasma. But one colossal question remained hanging in the silence of the cosmos. This entire event, this tidal disruption, was still just a ghost, a prediction born from theory. No one had ever seen it happen. If a star were truly torn asunder by a black hole's gravity, what would that cataclysm look like from a billion light-years away? What kind of celestial flare, what ephemeral blaze of glory would signal such an extraordinary and violent death? The hunt was on for a new kind of light in the universe, the fleeting death cry of a star at the moment of its annihilation. And so the theory remained locked in the sterile world of equations. A prediction of stellar death so complete, so absolute, it felt more like celestial myth than gravitational physics. For decades, the tidal disruption event was a ghost in the machine, a chilling piece of cosmic calculus whispered about in university halls and scribbled onto blackboards. But the universe has a habit of confirming our most violent imaginations. The question was no longer if these gravitational executions were happening, but how? How could we possibly catch a supermassive black hole in the act red-handed across an impassable gulf of millions of light-years? The challenge was almost laughably immense. Imagine trying to witness a single lightning strike happening for just a few months inside a storm cloud on the far side of the planet. Now imagine that storm cloud is a galaxy, 100,000 light-years across, and you have billions of them to watch all at once. The odds of being in the right place at the right time with a telescope pointed in the right direction were astronomically small. What astronomers needed was not just luck, but a new way of seeing, a way to monitor the entire cosmic ocean, not just a few square inches of it, for the faintest, most ephemeral ripple. For a time, the universe kept its secrets. We saw the steady churning maelstroms of active galactic nuclei, the so-called quasars, where black holes fed continuously from vast reservoirs of gas a constant luminous roar. We saw the brilliant explosive death of massive stars in supernovae detonations that could outshine their entire host galaxy for a few weeks before fading into memory. These were the known monsters, the familiar celestial beasts. But every so often, something else would appear in the data, something that didn't fit the established profiles. In the 1990s, the German X-ray satellite Rosat, while methodically mapping the sky, recorded bizarre flashes of high-energy light. These weren't from the usual suspects. They erupted from the very hearts of galaxies that were otherwise dormant, silent and unassuming. These were quiet galactic suburbs where suddenly, inexplicably, a siren of X-rays would scream into life blaze for a few months and then fade away into nothingness. It was a cosmic hit and run. These anomalous events were filed away, catalogued as curiosities, their true nature, a deep and tantalizing puzzle. They were whispers in the dark, the first clues that the theoretical ghost might have a physical body after all. To turn these tantalizing hints into irrefutable proof, we had to learn how to read the light from the crime scene. Scientists went back to the theoretical blueprint, the original equations, and sketched out a unique forensic profile. What would the murder of a star by a black hole actually look like? They predicted a very specific signature, an autograph written in radiation across the electromagnetic spectrum. First, there would be the flare itself, a cataclysmic brightening unlike anything else. As the star's constituent plasma was stretched into a cosmic noodle, shocked and compressed, it would heat to millions of degrees. This superheated gas, screaming in its death throes, would unleash a ferocious torrent of high-energy radiation, primarily in the ultraviolet and soft X-rays. This initial flash would be the herald, the gunshot echoing through the cosmos. But the true telltale sign, the definitive fingerprint, would be in how the light died down. Unlike a supernova, which explodes and fades in a relatively complex and rapid manner, the light from a TDE was predicted to follow a much smoother, more elegant trajectory of decay. As the trailing half of the stellar debris stream swung back around on its new elliptical orbit, it would fall onto the black hole at a predictable rate. The physics dictated that this fallback rate, and therefore the brightness of the accretion flare, should diminish over time following a very specific mathematical power law, fading in proportion to time to the power of -5/3. It was a beautiful, clean prediction. Finding a flare that dimmed with this precise cadence would be like finding a suspect's DNA at the scene. It was the smoking gun. But even that wasn't enough. The ultimate confirmation had to be written in the very elements being consumed. We needed an autopsy of the light itself. Using spectroscopy, astronomers could dissect the light from these flares, splitting it into its constituent colours, like a prism revealing dark or bright lines that correspond to specific chemical elements. A supernova's spectrum is a chaotic jumble littered with the spectral lines of heavy elements like oxygen, silicon and iron forged in the star's core and blasted out into space. A tidal disruption event, however, would be fundamentally different. It would be cleaner. The star being torn apart is typically a main sequence star like our Sun, composed overwhelmingly of the universe's simplest elements, hydrogen and helium. So the spectrum of a TDE should be dominated by the lines of hydrogen and helium stripped from the star's outer layers. Furthermore, these spectral lines would be incredibly broad. The gas in the debris stream would be moving at ferocious speeds, thousands of kilometers per second, some of it flying towards us, some of it away from us. This extreme range of velocities, a consequence of the black hole's immense gravity, would smear the spectral lines, stretching them out across the spectrum. A sudden flash of X-rays from a quiet galactic core, a flare that faded with a perfect power law decay, and a spectrum showing broad lines of hydrogen and helium, but a conspicuous absence of heavy elements. This was the triple-locked ironclad case for a TDE. Now all they had to do was find one. The breakthrough didn't come from one telescope, but from a new generation of them working in concert like a global detective agency. The hunt required Sentinels, trackers and forensic specialists. The Sentinels were the new ground-based wide-field surveys. Telescopes like the Zwicky Transient Facility in California and Pan-STARRS in Hawaii were not built to stare deeply into one small patch of sky. Instead, they were designed to do the opposite, to scan the entire visible heavens every few nights. They are relentless robotic guardians of the celestial sphere, creating a vast, moving map of the cosmos. Their software constantly compares the new images with older ones, looking for anything that has changed, anything that has appeared, disappeared, or changed in brightness. They are the ultimate neighbourhood watch, flagging anything that goes bump in the night. It was these surveys that began catching the initial optical glimmers of TDEs, the first visible light evidence that something was wrong in the heart of a distant galaxy. They would spot a new point of light, a transient, and automatically send out an electronic alert to astronomers across the world. The chase was on. Once the alert was sounded, the trackers would swing into action. The undisputed champion in this role was NASA's Swift Observatory. Launched in 2004, Swift was originally designed to hunt for the fleeting afterglows of gamma-ray bursts, the most powerful explosions in the universe. To do this, it was engineered with a remarkable ability. It could autonomously pivot and repoint its telescopes to a new target anywhere in the sky in less than a minute. It was a cosmic ambulance chaser built for speed and reaction. This unique talent made it the perfect instrument to follow up on the alerts from ground-based surveys. When a potential TDE was flagged, Swift could rapidly slew its instruments to the source, capturing the crucial early-time data in the ultraviolet and X-ray portions of the spectrum light that is completely blocked by Earth's atmosphere. Swift became the bridge connecting the initial optical flash seen from the ground to the high-energy scream that theorists had long predicted. Its ultraviolet optical telescope UVOT could map the evolution of the flare, while its X-ray telescope XRT could confirm the presence of that superheated gas, the primary signature of matter being accreted by a black hole. Then came the forensic specialists, the high-resolution eyes that could perform the detailed autopsy. NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton are the crown jewels of X-ray astronomy. where SWIFT provides the rapid response snapshot Chandra and XMM provide the deep penetrating high-definition analysis. With their exquisitely crafted mirrors, they can resolve the X-ray light with incredible sharpness, confirming with pinpoint accuracy that the flare is originating from the galactic nucleus, the lair of the supermassive black hole, and not from some foreground star or a background object. More importantly, their sensitive spectrometers can dissect the X-ray light with unparalleled precision, measuring the temperature of the accreting gas and searching for the subtle spectral features that tell the story of the star's demise. They act as the lead medical examiners, taking the initial data from the trackers and conducting the deep analysis that could definitively confirm the cause of death. It was this powerful synergy, the ground-based sentinels finding the suspects, the fast-moving SWIFT spacecraft tracking them down, and the powerful space-based observatories like Chandra conducting the in-depth interrogation that finally cracked the case wide open. In 2011, this global network caught a monster. SWIFT detected an extraordinarily bright and long-lasting burst of high-energy X-rays from a galaxy nearly 4 billion light-years away. The event catalogued as SWIFT J-Sulfurofas was unlike anything seen before. It wasn't just a thermal flare from accreting gas. This was something far more violent. As telescopes around the world and in orbit scrambled to observe it, a stunning picture emerged. The black hole hadn't just eaten a star, it had used the stellar remains as ammunition. The event had launched a powerful focused jet of particles screaming outwards at nearly the speed of light. This relativistic jet, a celestial blowtorch of unimaginable power, was pointed almost directly at Earth. For over a year, this jet flickered and flared, powered by the steady rain of stellar debris falling onto the black hole. It was as if we were witnessing the birth of a temporary miniature quasar ignited by the sacrifice of a single unlucky star. SWIFT J-Sulfurofas was a revelation. It proved not only that TDEs happened, but that they could be far more diverse and powerful than the simplest models had predicted. It showed that the process of shredding a star could organize magnetic fields and launch outflows with an efficiency that rivaled the most powerful objects in the universe. In the years that followed, the floodgates opened. Armed with the knowledge of what to look for, astronomers began combing through archival data and hunting for new events with ruthless efficiency. They found TDEs in the optical-like Assassin 14LA, an event so bright and relatively close that telescopes could watch its debris cloud evolve over months, its spectrum showing the telltale broad helium and hydrogen lines. They found TDEs that were rich in X-rays but faint in visible light, and others that were bright in visible light but strangely silent in X-rays, hinting at a complex geometry where a thick shroud of outflowing gas might be obscuring our view of the central engine. Each new discovery was another piece of the puzzle, another entry in the growing bestiary of stellar death. They found evidence of stars being only partially disrupted, surviving their first pass by the black hole, only to be wounded and bled out over subsequent orbits. They confirmed time and again the predicted T to the -5/3 decay law, seeing it etched into the fading light curves of dozens of events. The ghost in the machine was finally cornered. The theoretical predictions born from the minds of physicists decades earlier were now being confirmed with astonishing fidelity in the real universe. The evidence was overwhelming, the case closed. We were without a doubt watching stars being torn apart. The shift from theory to observation was complete. We had transitioned from an era of speculative calculation to an era of empirical observational fact. Tidal disruption events were no longer a fringe theory. They were a confirmed and vital new window into the unseen universe. We had developed the tools and techniques to catch these fleeting violent acts in real time, to diagnose them from across billions of light years, and to begin building a catalogue of these gravitational atrocities. The breakthrough was not merely in confirming their existence, it was in the sudden stunning realization of what this discovery now enabled. For every star that is destroyed provides a unique momentary gift. Its death illuminates the darkness, sending out a final flare of information from a region of space-time that is otherwise eternally silent and inscrutable. We were no longer just passive observers of galactic violence. We were becoming cosmic archaeologists using the shattered remains of stars to probe the properties of their executioners. Now that we could find them, now that we could watch them unfold, the truly profound questions could finally be asked. What secrets do these dying screams carry about the monsters that are responsible? What can the final moments of a star teach us about the nature of gravity, the spin of a black hole, and the very fabric of space and time at the edge of the abyss, and so the star's final graceful arc delivers it to the precipice? We have tracked its cosmic ballet, a dance choreographed by gravity across millions of years leading to this one singular irrevocable moment. There is no physical wall here, no shimmering barrier in the void. There is only a line of absolute consequence and invisible circumference of doom known as the tidal radius or the Roche limit. Crossing this boundary is not like passing through a doorway. It is like being the river that reaches the waterfall. The physics of the universe, patient and unyielding, is about to assert its ultimate authority. What happens next is not an explosion, not a collision in the conventional sense. It is a dismantling, an unmaking. It is the beginning of a process so strange, so violent, and so utterly alien to our human experience that it has earned a name from the realm of caricature spaghettification. To understand this celestial execution, you must first unlearn a fundamental intuition. We think of gravity as a uniform force pulling us down to the Earth with a consistent grip. But a black hole's gravity is a different beast entirely. It is a force of unfathomable gradients, a slope of space-time so steep that every millimetre of distance matters. The key to the star's destruction lies not in the sheer power of the black hole's pull, but in its brutal inequality. This is the principle of differential gravity, and for the approaching star, this simple physical truth becomes a death sentence. Imagine yourself falling towards such an object. The gravitational pull on your feet would be exponentially stronger than the pull on your head. You wouldn't simply fall, you would be stretched, your body elongated by this cosmic tug-of-war playing out across your own frame. Now scale that experience up to the colossal dimensions of a star, a sphere of incandescent gas millions of kilometers in diameter. As our star crosses the Roche limit, the side facing the black hole, its stellar shore is seized by a gravitational grip that is titanically stronger than the force clutching its far side. The star is placed upon a gravitational rack. The initial effect is subtle, a slight distortion of its perfect spherical form. It begins to bulge, pulled into the shape of a teardrop, its leading edge pointing toward the abyss. This is the point of no return made manifest. The star's own self-gravity, the force that has held it together in a stable luminous equilibrium for billions of years, is now in a losing battle. The black hole's differential pull has become the dominant force in the star's existence. Its internal structure, once a delicate balance of pressure and fusion, begins to fail catastrophically. Layers of hydrogen and helium held in place for eons feel the strain. The star moans not in sound but in gravitational waves, faint whispers of its agony rippling across the fabric of space-time. Through our most advanced simulations, we can witness the horrifying beauty of this deconstruction. The teardrop shape becomes unstable, the point elongating, stretching further and further. The star is being unspooled like a celestial ball of yarn. Plasma superheated to millions of degrees begins to bleed from its leading edge, a torrent of stellar material siphoned away into the void. This isn't a gentle process, it is a shredding. The immense tidal forces create shock waves that propagate inward, tearing through the star's convective and radiative zones, disrupting the very engine of its core. The star loses its identity. It is no longer a cohesive body, but a distended, flowing filament of its former self. Within hours, a process that takes nature millions of years to build is utterly unmade. The spherical giant becomes a flowing cosmic noodle, a luminous river of gas thousands of times longer than it is wide one end already, disappearing into the swallowing darkness, while the other is still anchored to the disintegrating bulk of the star. This is spaghettification in its full terrible glory. The star's constituent atoms are separated, its magnetic fields are twisted into chaotic braids, and its once stable core is ripped open, exposing material that has not seen the light of the cosmos since the star's birth. Yet here we encounter one of the most profound revelations in this entire saga of destruction. The black hole is not an efficient eater. The process is violent, but it is also messy, governed by the precise laws of orbital mechanics. This long, thin stream of stellar material does not simply plunge directly into the event horizon. The star in its final orbit possessed a tremendous amount of angular momentum, a sideways motion that it doesn't simply lose. As the material is stripped away, it inherits this momentum. Think of a comet whipping around the sun. It doesn't fall straight in, but slingshots around its path dictated by speed and angle. The stellar stream does the same. Consequently, the fate of the star is cleaved in two. Roughly half of the material, the part that was on a trajectory taking it too close too directly, lacks the momentum to escape. Its journey is short and brutal. It crosses the event horizon and is lost from our universe forever, its mass and energy added to the silent ledger of the singularity. But the other half, a vast river of plasma containing the mass of hundreds of thousands of Earths, finds itself on a slightly different path. It has enough sideways velocity to whip around the black hole, overshooting the point of oblivion. This material is now gravitationally bound, captured in orbit, but it has escaped immediate annihilation. It is destined not for a quick death, but for a lingering incandescent purgatory. This surviving stream of gas, this stellar ghost, embarks on a new elliptical orbit, a long, looping journey that will eventually bring it back toward the very monster that destroyed its parent star. And when it returns, the real fireworks begin. The leading edge of this returning stream, having completed its first perilous orbit, slams into the tail of the stream that is still falling inward for the first time. It is a collision of unimaginable scale and energy. Two currents in this river of plasma, moving at a significant fraction of the speed of light, smash into one another. The result is a shockwave of monumental proportions, a cosmic traffic jam, where the kinetic energy of motion is explosively converted into heat. This intersection point, known as the pericenter, becomes the crucible for one of the universe's most luminous creations. The friction is immense, a grinding of plasma on plasma that acts as a powerful brake. The gas can no longer maintain its long elliptical orbit. It loses energy, its path decaying, tightening, and beginning to circulate. What we are witnessing is the birth of an accretion disk. The orderly stream devolves into a chaotic, swirling vortex of superheated gas. Piece by piece, fragment by fragment, the remnants of the dead star settle into a flattened, rapidly rotating disk around the black hole's equator. This is no gentle carousel. It is a maelstrom of violence. Gas parcels jostle and shear against each other, and this friction, this cosmic viscosity, generates heat on a scale that dwarfs the star's own thermonuclear furnace. The plasma in the inner regions of this nascent disk is flash-heated to millions, sometimes tens of millions of degrees hotter than the core of the star from which it came. In this inferno, atoms are stripped of their electrons and powerful magnetic fields dragged along from the star, and now twisted and amplified by the disk's rapid rotation, are generated. These fields create even more friction, more turbulence, driving the temperatures and pressures to unimaginable extremes. The once dark region around the invisible black hole is set ablaze. The accretion disk begins to glow, not with the gentle, steady light of a star, but with a ferocious high-energy radiance. It shines with an intensity billions of times greater than our own sun. A cosmic beacon is ignited where there was once only darkness. The black hole, the agent of destruction, has inadvertently created a temporary miniature quasar, a blazing testament to the star it just consumed. This is the pivotal twist in our story. The death of the star is not an ending. It is a transfiguration. The quiet, predictable hydrogen-fusing sphere is gone, and in its place is a dynamic, chaotic, and brilliantly luminous engine of cosmic power. The star's matter, liberated from its gravitational cage, has been repurposed into a celestial blowtorch that will outshine entire galaxies, if only for a fleeting cosmic moment. The timescales are dizzying. The spaghettification itself, the primary act of destruction, might take only a matter of hours or days. The formation of the disk and the subsequent rise to peak brightness can unfold over weeks or months. For a brief period, a few years, perhaps a decade, this accretion disk will blaze a memorial pyre fueled by the star's remains. The light generated by this process is immense, a desperate flare visible across billions of light years. It is a scream of radiation, a final shout into the cosmic darkness that carries with it an extraordinary wealth of information. This light is a fingerprint, a detailed forensic report of the star's final moments. It tells us about the star's mass and composition, and more importantly, it illuminates the very object responsible for its demise. The black hole, which by its nature cannot be seen, is now silhouetted by the brilliant ruin of its last meal. It is wearing a crown of fire. We are no longer just watching a star die. We are watching the birth of a laboratory. This incandescent disk, this swirling symphony of chaos, offers us an unprecedented opportunity. For the first time, we have a source of light originating from the very edge of a supermassive black hole's domain, a region of space-time we could never hope to probe directly. Every photon launched from this searing vortex carries secrets about the black hole's mass, about its spin, even about the warped nature of space-time in its immediate vicinity. The destruction, as total as it was, has created a window. But what exactly do we see when we look through that window? What languages does this brilliant, fleeting light speak? And what tales does it tell of the gravitational titan hiding within that fiery shroud? The beacon has been lit, and now, across the vastness of the cosmos, our telescopes turn to read the message written in the star's dying light. The star is gone. In its place, a river of fire now arcs through the absolute blackness, a luminous scar tracing the path of a ghost. Half of the star's mass flung away by the catastrophic encounter sails into the interstellar void as an unbound fading streamer. But the other half, the portion that passed just a little too close, remains captive. It has been caught by the monster's gravitational snare, its momentum stolen, its fate sealed. This colossal filament of stellar plasma, millions of kilometers long yet impossibly thin, cannot escape. It is a celestial boomerang thrown with cosmic violence, now beginning its long inevitable fall back toward its destroyer. This returning stream is not a simple plunge. It carries with it the orbital energy it possessed just moments before its demise, a memory of its former life as a star. As it swings back around the black hole, its path is a looping eccentric ellipse, a wounded orbit that brings it perilously close to its own trailing tail. Here in the warped space-time near the singularity, a second cataclysm unfolds, one born not of gravity but of collision. The leading edge of the stellar debris, having completed its first perilous passage, slams into the material still falling inward for the first time. It is a process of cosmic recycling on the most brutal scale imaginable. And from this violent self-collision, a new structure begins to coalesce. Shockwaves of unimaginable power propagate through the gas, cancelling out its wild elliptical motion and forcing the material to settle. This is the painful birth of an accretion disk. It is no serene planetary nursery like the one that formed our own solar system. This is a maelstrom of incandescent plasma, a temporary violent whirlpool swirling around the drain of space-time. The stellar material, robbed of its star, now loses its very identity, smeared out into a spinning platter of fury and light. The star's orderly sphere has been metamorphosed into a chaotic, transient ring of torment, a final glowing monument to its own destruction. Every particle within it, once part of a fusion-powered core or a tranquil photosphere, is now trapped in a frantic gravitational dance spiraling ever closer to the point of no return. As this nascent disk forms and flattens, it becomes one of the most luminous objects in the universe. The light we see, the flare that announces the star's death across millions of light years, is not the explosion of the star itself. It is the glow of its own remains being tortured. Deep within the disk, immense friction and turbulent magnetic fields act like a cosmic grindstone. Layers of gas moving at slightly different speeds shear against one another, generating heat on a scale that dwarfs any star's core. The plasma is compressed and twisted, its temperature soaring not to thousands but to millions of degrees. It is a celestial blowtorch powered by the inflow of matter, converting the raw gravitational potential energy of the star's corpse into a blinding torrent of radiation. Imagine looking down upon this structure. It would appear as a cosmic bullseye of impossible heat. The outer edges of the disk cooler and more diffuse glow, with the familiar light of the optical spectrum a ghostly echo of the star's original colour. Moving inward, the temperature climbs relentlessly. The glow shifts, becoming a searing blue, then an intense lethal ultraviolet. This is the region that dominates the initial brilliant flash of a tidal disruption event, a beacon that can briefly outshine every star in its host galaxy combined. But the true violence is reserved for the innermost edge, the last stable orbit before the abyss. Here, just scant miles from the event horizon, the plasma shrieks at temperatures exceeding 10 million degrees Celsius. It can no longer emit visible light. Its agony is broadcast in the high-energy language of X-rays, a piercing invisible scream that tells of matter on the brink of oblivion. For months, sometimes years, this accretion disk will churn. It is a slow, agonizing drain. The gas doesn't fall straight in. It spirals inch by painstaking inch, losing energy, with every rotation its orbit decaying as it surrenders its heat to the cosmos, in the form of this spectacular multi-wavelength flare. We watch from our telescopes on Earth 250 million light-years away or more, and we see this light signature rise and fall. We see the colour of the flare evolve, shifting from the hot blue UV to the cooler, redder optical, as the disk expands and thins. The fading light curve follows a predictable pattern, a tale of diminishing returns as the finite fuel source, the remains of that one unlucky star, is steadily consumed. Each photon that reaches our detectors is a messenger from this gravitational purgatory, a final testament from matter just before it is erased from the universe. We are in essence witnessing the black hole feeding in slow motion, the grandest and most terrible feast in the cosmos. And as the last wisps of stellar plasma complete their death, spiral as they slip across the event horizon and their light is forever extinguished, the flare subsides. The galaxy returns to its quiet slumber, the black hole once again cloaked in a perfect patient darkness. The evidence of the crime slowly fades, leaving only a subtle warmth in the void. This for a long time was the story we thought we understood. A star is shredded, a disk is formed, a brilliant flare is launched, and then silence. It was a picture of elegant, predictable violence. But the universe, as it so often does, refused to conform to our tidy narrative. As our telescopes grew more sensitive as we began to catch these fleeting events with greater frequency, a profound and perplexing mystery began to emerge. The aftermath was not always the same. Some tidal disruptions, the majority in fact, followed the script. They produced the glorious thermal flare of a superheated accretion disk, a temporary lighthouse in the cosmic dark. But others did something far more dramatic. They produced something we'd seen before, but only in the most extreme active galactic nuclei. Powerful, tightly collimated jets of material blasted away from the black hole at nearly the speed of light. Suddenly, the crime scene was not just illuminated by the glowing embers of the victim. It was the site of a colossal particle accelerator, a cosmic cannon firing relativistic bullets across intergalactic space. These jets, detected as brilliant flashes of radio waves and high-energy gamma rays, represented a completely different physical process. The thermal glow of the accretion disk is chaotic, radiating its energy in all directions like a bare light bulb. A jet, however, is an ordered, focused, and terrifyingly energetic structure. It meant that in some of these events, the black hole wasn't just passively feeding on the stellar debris. It was actively seizing that infalling matter and energy, and using it to launch a colossal outflow that could travel for thousands of light years. The star's death was not just fueling a bonfire, it was loading and firing a weapon of galactic proportions. This discovery shattered our simple understanding and plunged the field into a deep and fascinating state of confusion. We were faced with a fundamental question: why? Why do some tidal disruption events, perhaps 1 in 100, produce these spectacular relativistic jets while the vast majority do not? The initial conditions seem so similar: a star, a supermassive black hole, a close encounter. Yet the outcomes are wildly, violently different. It's like discovering that striking two identical matches sometimes produces a gentle flame, and other times a directed explosion. Something crucial, some hidden variable must be at play, dictating the final explosive fate of the stellar remains. The search for this hidden variable has become one of the central quests in high-energy astrophysics. The prime suspect is the black hole itself. We tend to think of black holes as simple objects defined only by their mass, but they possess another fundamental property, one bequeathed to them by the stars and gas that collapsed to form them, or that they have since consumed: spin. Just as a planet or a star rotates, so too can a black hole. And a spinning black hole is a far more complex and dynamic beast than a stationary one. Its rotation is so extreme that it literally drags the fabric of space-time around with it, a phenomenon known as frame dragging. This creates a region outside the event horizon called the ergosphere, a cosmic whirlpool of space-time itself. Within this region, nothing can stand still. Everything is forced to rotate with the black hole. It is a place where the rotational energy of the singularity is immense, a colossal reservoir of power waiting to be tapped. Here a tantalizing theory begins to form. Perhaps the presence of a jet is a direct consequence of a rapidly spinning or pure black hole. In this model, the accretion disk formed from the shredded star becomes threaded with powerful magnetic fields, the star's own magnetic field amplified and tangled by the violent formation of the disk. As this magnetized plasma spirals into the ergosphere, the spinning space-time grabs hold of these magnetic field lines. It twists them into a tightly wound colossal helix, like winding up a gigantic rubber band. This process, known as the Blandford-Znaiec mechanism, can extract the black hole's rotational energy and convert it into a focused outbound particle beam. The magnetic fields act as a conduit, channeling the power of the black hole's spin into two oppositely directed jets that erupt from the poles of the disk. In this scenario, a non-spinning or Schwarzschild black hole simply lacks the dynamic engine required for this process. It can still accrete matter, it can still power a brilliant thermal flare from its disk, but it has no rotational energy to donate, no swirling space-time to twist the magnetic fields into a particle cannon. The black hole's spin then could be the critical switch. A high spin rate means jets, a low or zero spin rate means only a flare. The star's fate and the nature of its luminous elegy would depend not just on its path, but on the ancient intrinsic nature of the very monster that consumes it. It's a beautifully compelling idea, linking the observable fireworks to the unseeable fundamental properties of the singularity. But even this elegant solution might be too simple. Other factors could be just as crucial, working in concert with the black hole's spin. The orientation of the star's orbit, for instance, could play a decisive role. If the star's orbital plane is perfectly aligned with the black hole's equator, the resulting disk will be orderly and flat. But what if the star arrives on a tilted or even a polar orbit? The resulting disk would be warped and torn by the frame-dragging effect, leading to far more complex interactions and magnetic field geometries. It's possible that this misalignment is a necessary ingredient, a way to more efficiently feed magnetic flux into the polar regions where these jets are launched. A well-behaved equatorial disk might be less effective at tapping the black hole's spin, even if the spin is rapid. Furthermore, the strength and structure of the magnetic fields themselves are a wild card. Did the original star possess an unusually powerful magnetic field? Was it amplified to extraordinary levels during the disruption and disk formation? A jet is at its heart a magnetic phenomenon. Without a strong, ordered magnetic field to act as the scaffolding and the accelerator, there can be no jet, no matter how fast the black hole spins. Untangling these interconnected possibilities, spin orientation magnetic flux, is a monumental challenge. Each tidal disruption event we witness is a single cosmic experiment, and we only see the outcome. Our task is to reverse engineer the cause from the faint fading light that reaches us across the eons. To do this, we have assembled a global network of silent partners. Our observatories work in unison, performing a kind of cosmic autopsy from afar. When an optical survey telescope like the Zwicky Transient Facility first spots the telltale flare of a new TDE, an alert flashes across the globe. Immediately, other telescopes pivot to stare at this new fleeting point of light. X-ray observatories like Chandra and XMM Newton search for the high-energy shriek from the inner edge of the disk, probing the region closest to the event horizon. Simultaneously, radio telescopes like the Very Large Array listen intently. They are searching for the characteristic delayed brightening, the synchrotron afterglow, that signals the presence of a new jet ploughing through the circumnuclear medium. By combining this multi-wavelength data, we can begin to build a complete picture of the event. The X-ray emission can give us clues about the accretion rate, and perhaps even the black hole's spin, as certain rapid flickering patterns, known as quasi-periodic oscillations, are thought to arise only in the swirling space-time around a spinning black hole. The radio data is our smoking gun for a jet. If we see a powerful radio source emerge days or weeks after the optical flare, we know we are witnessing one of those rare jet-producing events. We can then compare the properties of the jetted TDEs to the non-jetted ones, hunting for systematic differences for the telltale signature of that hidden variable. The work is slow, painstaking, and exhilarating. Each new event is another clue, another piece of a puzzle scattered across the entire observable universe. We are like cosmic detectives arriving late to the scene, sifting through the faint ethereal evidence to reconstruct a crime of unimaginable violence. The mystery of the jets is more than just a question of celestial mechanics. It touches upon the very nature of black holes and their role in the cosmos. These events are not just acts of destruction, they are fleeting laboratories. They provide us with a rare momentary probe into the extreme physics near an event horizon, an environment otherwise forever hidden from our direct view. What we learn here in the fading light of a dead star will teach us not only how they die, but how the enigmatic engines at the heart of every galaxy truly work. And so, we have witnessed a star's final silent scream. A magnificent incandescent body which for billions of years had sailed the tranquil seas of its home galaxy has been unwritten from the cosmos. We have followed its ill-fated journey into the gravitational abyss, watched its form distend and tear, and seen its substance spun into a swirling superheated ghost. From our distant vantage point, this act of celestial violence appears absolute a brutal endpoint to a stellar life story. It seems like nothing more than a funeral pyre, a monument to the unforgiving power of a supermassive black hole. But this is where the story truly pivots. This is where destruction gives way to revelation. Because that brilliant fading flare of light, the last testament of a dying star, is not an ending. For us it is a beginning. It is a message in a bottle cast out from the edge of an event horizon, carrying secrets that would otherwise remain forever locked away in darkness. This cataclysm, this ephemeral beacon burning for a few months or years in the heart of a distant galaxy, is an extraordinary gift. It transforms the monster of the deep into a subject of study, converting a passive, invisible behemoth into an active, illuminated laboratory. The star's sacrifice is not in vain. Its demise becomes our Rosetta Stone, allowing us to decipher the fundamental properties of the universe's most enigmatic objects. We simply have to learn how to read the light. Our primary tool in this cosmic forensic investigation is deceptively simple: a graph, a plot of brightness against time. We call it a light curve. Yet this simple line on a chart is the star's autobiography written in its final moments. It is the EKG of a cataclysm. As the first streams of stellar material fall back and collide with themselves, they ignite, and the light curve spikes soaring upwards to a peak of unimaginable brilliance. This initial breathtaking crescendo tells us about the violence of the collision, the sheer density of the stellar debris being slammed together at a fraction of the speed of light. It is the moment of ignition in the universe's most powerful engine. Then, after reaching its zenith, the light begins to fade, but it does not simply vanish. It decays in a very specific, predictable way. According to theoretical models, the brightness should fall off in proportion to time, raised to the power of -5/3. This precise mathematical relationship is the first great clue. It represents the rate at which the stellar material, the long spaghettified stream, continues to fall back onto the black hole over months and years. By carefully tracing this decline, by matching the shape of this fading echo to our models, we can perform a truly staggering feat of cosmic accounting. We can weigh the black hole. Imagine trying to weigh an object you cannot see from billions of light years away, an object whose defining characteristic is that it consumes everything, even light. It seems impossible. Yet the physics of the stellar fallback rate is intimately tied to the gravitational field of the central object. A more massive black hole with its more powerful gravity will pull the stellar debris back more quickly, causing the flare to rise and fall over a shorter timescale. A less massive black hole will have a more leisurely influence, resulting in a TDE that evolves more slowly, its light curve stretched out over a longer period. Each light curve is therefore a unique gravitational signature. The duration of the flare, the shape of its decay, all of it is encoded with the mass of the monster responsible. For the first time, we have a scale forged from the physics of a shredded star capable of measuring these hidden titans. We are no longer just guessing, we are measuring. And this technique opens a whole new window into the universe. Most other methods for weighing supermassive black holes rely on observing the motions of stars or gas clouds orbiting far from the centre, a process that works well for nearby active galaxies. But what about the countless quiet galaxies where the central black hole is dormant, starved of fuel? They are invisible. A TDE is like a sudden flashbulb illuminating a dark room. It allows us to detect and weigh the silent majority of supermassive black holes, the sleeping giants that populate the hearts of perhaps every large galaxy, including our own. We are building a census, a demographic survey of the universe's largest gravity wells, one stellar death at a time. Each new event adds a data point to our map, refining our understanding of how these objects grow and how they relate to the galaxies they inhabit. The M-sigma relation, that fundamental link between a black hole's mass and the velocity of stars in its host galaxy's bulge, can now be tested in previously inaccessible corners of the cosmos. But the light curve is only the first chapter of the story. To uncover the deeper secrets, we must become cosmic chemists and physicists. We must take the light from the flare and pass it through a prism, a spectrograph, shattering it into its constituent colours, its rainbow spectrum. This spectrum is a barcode rich with information about the maelstrom at the galaxy's core. Imprinted upon this band of light are dark absorption lines and bright emission lines, each one a chemical fingerprint left by atoms caught in the celestial crucible of the accretion disk. Here we can read the very composition of the devoured star. We can see the telltale signatures of hydrogen and helium, the primary constituents of most stars. Sometimes we see traces of heavier elements like nitrogen or carbon offering clues about the star's age and evolutionary history. We are performing a stellar autopsy from across the universe, determining the nature of the victim long after it has ceased to exist. These spectral lines do more than just identify elements. They reveal the physics of the abyss. The lines are not sharp and precise as they would be in a calm laboratory setting. They are broadened and smeared out, a direct consequence of the extreme velocities inside the newly formed accretion disk. Some of the stellar gas is whipping towards us at thousands of kilometers per second, causing its light to be blue-shifted. An equal amount is racing away from us, its light red-shifted towards the red end of the spectrum. This Doppler broadening paints a vivid picture of a disk of material spinning furiously, a gravitational vortex of incandescent plasma. By measuring the width of these lines, we can calculate the speed of the orbit, and in doing so, we can probe the structure of the innermost accretion flow, the final pathway for matter on its one-way trip into the black hole. We are watching in real time the assembly of the very structure that will feed the black hole for years to come. In some TDEs, we see something even more profound. We see spectral lines that are not just broadened but have complex evolving shapes. We might see a double-horned profile, the signature of a well-ordered flattened disk, one horn from the approaching side and one from the receding side. In other events, the lines are more chaotic, suggesting a puffier, more turbulent flow of gas. Sometimes we detect powerful outflows, winds of stellar material being blasted away from the disk by the intense radiation revealed by blue-shifted absorption features that tell us gas is being ejected directly towards our line of sight. These winds are of colossal importance to galaxy evolution. They are one of a major mechanism by which a supermassive black hole can influence its host pumping energy and chemically enriched material back into the galaxy, and potentially regulating future star formation. A TDE in its brief violent life allows us to witness this feedback process in action, a process that is otherwise almost impossible to observe directly in dormant galaxies. The shredded star becomes a tracer illuminating the complex relationship between a black hole and its galactic kingdom. This brings us to one of the most sought-after prizes in all of astrophysics, a measurement of a black hole's spin. According to Einstein's theory of general relativity, a black hole is defined by only three properties: its mass, its electric charge, which is thought to be negligible, and its angular momentum or spin. We have learned how to measure its mass, but its spin that is a far more subtle and elusive quantity. A spinning black hole does not just curve space-time, it twists it. It drags the very fabric of the universe around with it in a cosmic whirlpool, an effect known as frame dragging, or the lens-Thirring effect. Anything falling into a spinning black hole is forced to spiral in its orbit, warped by this powerful gravitomagnetic force. A TDE provides a unique opportunity to see this twisting of space-time made manifest. The stellar debris does not fall neatly into the black hole's equatorial plane. The star can approach from any angle. If the black hole is spinning, the newly formed accretion disk will be misaligned with the black hole's spin axis. The immense torsional force of the twisting space-time will then act upon this disk, trying to pull it into alignment. The disk doesn't just snap into place. Instead, it wobbles. It precesses like a tilted gyroscope trying to right itself. This grand relativistic wobble of the entire inner accretion disk, a disk spanning millions of kilometers, should produce a quasi-periodic signal. As the disk precesses our view of the hottest innermost regions, changes causing the X-ray and UV light emitted from the TDE to vary on a predictable timescale, rising and falling in a rhythmic pulse. Detecting such a signal, these quasi-periodic oscillations or QPOs, is the holy grail of TDE science. Several promising candidates have been found rhythmic flickers in the X-ray light from a tidal disruption, repeating every few hours or days. If these signals are confirmed to be the signature of lens-Thirring precession, they will be one of the most direct and stunning confirmations of general relativity in the strong field regime. More than that, they will give us a direct handle on the black hole's spin. A faster spin creates a stronger frame dragging effect, causing the disk to precess more rapidly and producing a shorter period oscillation. A slower spin leads to a more leisurely wobble. By timing these cosmic pulses, we can measure the rate at which the universe itself is being twisted by the black hole's rotation. The spin of a black hole is not just a curiosity, it is a fossil record of its entire life. A black hole born from the collapse of a single star should have a relatively modest spin. A supermassive black hole that grew primarily by consuming gas that spiraled in gently from a large accretion disk over billions of years should be spun up to near the maximum possible rate. But a black hole that grew through chaotic mergers with other black holes, each coming in from a random direction, might have its spin slowed down or even reversed. Measuring the spins of a population of black holes across the universe would therefore tell us how they grew. Did they grow through orderly accretion or violent chaotic mergers? This is one of the biggest unanswered questions in galaxy evolution. The final dying shriek of a star as its light flickers to the rhythm of precessing space-time may hold the key. Finally, the light from a TDE must undertake one last journey before it reaches our telescopes. It must travel out from the galactic nucleus through the immediate environment surrounding the supermassive black hole. This region, the circumnuclear medium, is a complex ecosystem of gas clouds, dust lanes, and older stellar populations. By analysing the TD's light, we can look for the fingerprints of this intervening material. We can see absorption lines from cool gas clouds that happen to lie along our line of sight, allowing us to map the distribution and kinematics of material in a region that is normally shrouded in darkness. Sometimes we see evidence of a dusty torus, a donut-shaped ring of material that is thought to surround many active galactic nuclei, which can absorb and re-radiate the TD's light at infrared wavelengths, creating a light echo that arrives months or years after the initial flare. The star therefore acts as a probe, a flashlight that suddenly switches on, briefly illuminating the architecture of the galactic core. Each TDE provides a core sample, a single line of sight through this complex environment. By observing dozens of these events, we can begin to build up a three-dimensional picture of what the centers of dormant galaxies actually look like. We can answer questions about how much fuel is available for the black hole, how it is distributed, and how it flows. We are not just studying the black hole in isolation, we're studying it within its native habitat, understanding its connection to the galactic structures it has helped to build over cosmic time. So when we look at the fading glow of a tidal disruption event, we must look past the violence. We are not seeing a simple explosion. We are seeing the birth of a cosmic laboratory. We are witnessing the conversion of a star into pure information. The light curve tells us the black hole's mass. The spectrum reveals the stellar composition and the physics of the accretion disk. The periodic flickering of its X-rays may one day give us its spin, and its passage through the galactic nucleus maps the unseen environment. This is the profound legacy of a TDE. It is not an act of pure destruction, but an act of stunningly powerful illumination. The star's death gives us an unprecedented, intimate look at the monster in the dark, transforming it from a theoretical abstraction into a measurable physical object. It is a tool of exquisite precision gifted to us by gravity itself. And as our telescopes scan the skies, finding more and more of these ephemeral cosmic lighthouses, we are piecing together the life story of supermassive black holes, and with it the story of the universe they command. The star is gone, but its final broadcast is only just beginning to be understood. And so we arrive here at the edge of this maelstrom, having journeyed from a realm of pure thought, from the elegant, terrifying calculus scribbled on a blackboard, to the raw, unfiltered light of a dying star. We began with a ghost in the equations, a mathematical premonition of what must happen when a star wanders too close to the abyss. It was a concept born in the quiet minds of pioneers who dared to follow the logic of relativity to its most violent conclusion. For decades, that is all it was, a theoretical curiosity, a piece of cosmic grand guignol confined to academic papers, a dark fable of the cosmos whispered among astronomers. There were no photographs, no data points, no tangible proof, only the stark, unblinking certainty of the physics. A black hole, they predicted, was not merely a passive sinkhole, but a predator armed with the most powerful weapon in existence, the warped geometry of space-time itself, and a star, that majestic nuclear furnace, that symbol of stability and light, could be reduced to a transient smear of incandescent plasma. Looking back from where we stand now, surrounded by a flood of data, it is difficult to fully grasp the audacity of that vision. We have watched robotic eyes pivot across the heavens, catching the first desperate flare of a tidal disruption event. We have seen the unblinking gaze of Swift capture the initial searing flash of high-energy X-rays, the star's first scream. We have witnessed observatories from Chile to Hawaii perform a delicate coordinated dance across continents and oceans, mapping the fading afterglow in visible and infrared light, piecing together the chemical fingerprint of the stellar debris. Radio telescopes' vast arrays of steel and silicon have listened patiently for the faint delayed whisper of a jet, the final exhalation of the cataclysm, punching its way out from the black hole's chaotic maw. This journey from abstraction to observation is one of the great intellectual sagas of our time. It is a testament to human ingenuity and our relentless, unquenchable need to know what lies out there in the dark. We built machines capable of seeing the invisible, of capturing photons that have travelled for hundreds of millions of years, carrying with them the precise story of a star's final moments. We transformed a theoretical nightmare into a working laboratory, a cosmic crime scene from which we could reconstruct the event, identify the victim, and profile the culprit. Each new detection, each light curve meticulously plotted, each spectrum painstakingly analysed has been a vindication of those early daring ideas. But they have also been so much more. They have been a profound revelation, forcing us to fundamentally reshape our understanding of the universe's most enigmatic objects. Before this era of discovery, the supermassive black holes at the hearts of galaxies were seen as largely dormant beasts. They were gravitational anchors, silent monarchs holding their courts of stars and gas in a quiet, orderly dance. Most of them in our cosmic neighbourhood seem to be sleeping, their great appetites sated, their influence felt but not seen. We knew they'd grown to their colossal size by feeding, but the process was thought to be a slow, steady accretion, or the dramatic but rare merger of entire galaxies. Tidal disruption events have shattered that placid image forever. They have shown us that these sleeping giants are not sleeping at all. They are waiting. They have revealed that the heart of a galaxy is not a sanctuary, but a treacherous, dynamic, and profoundly dangerous place. The calm can be broken in an instant. A single star on a billion-year orbit makes one wrong turn, and the silent monarch awakens in a blaze of glory. Suddenly the black hole is no longer just a static data point, a mass, a spin, an event horizon. It is an active, violent engine. The TDE provides a momentary, brilliant illumination of what is otherwise an eternally dark stage. For a few months or a few years, the shredded star forms a temporary accretion disk, a luminous halo of superheated gas swirling into the void. This disk, this death spiral, becomes a diagnostic tool of incredible power. Its light allows us to weigh the black hole with astonishing precision confirming the existence of monsters 1 million to 1 billion times the mass of our own Sun. The subtle flickers and wobbles in that light, the so-called quasi-periodic oscillations we have witnessed, are the signature of the black hole's own ferocious gravity, a gravitational gyroscope spinning at nearly the speed of light. We are not just seeing the remnants of a star, we are seeing the direct dynamic influence of the black hole's spin, a property once relegated to the deepest realms of theoretical physics. We are watching in real time as the fabric of space-time itself is twisted into a vortex. The star becomes a sacrificial probe sent on a one-way journey to the very edge of reality, and its dying light is the final report it sends back to us. This has torn down the wall between black holes as theoretical constructs and black holes as observable physical objects with complex personalities. They are not all the same. Some spin furiously while others are more sedate. Some produce those astonishing relativistic jets we have seen, cosmic blowtorches that channel the energy of an entire star into 2 needle-thin beams of particles and radiation. Others, for reasons we are still desperately trying to understand, seem to swallow their meal with barely a whisper. TDEs are the ultimate cosmic autopsy. By studying the remains, we learn about the life of the star, its chemical composition, its internal structure just before it was so completely unmade. We also learn about the environment around the black hole, the dust and gas that may have shrouded it for millennia, which is now flash ionized and illuminated by the event. But perhaps the most profound shift in our perspective is the realization that this incredible violence, this act of supreme cosmic destruction, is not an ending. It is also a beginning. We are conditioned to see destruction as a terminal act, a descent into chaos and disorder. But the universe in its grand indifferent wisdom is a master of recycling. A TDE is not just a funeral pyre, it is a celestial forge. As the stellar material is whipped into a frenzy in the accretion disk, it is heated to millions of degrees. Elements are stripped of their electrons, subjected to pressures and temperatures unimaginable in the core of even the most massive star. This process can trigger nucleosynthesis, the creation of new heavier elements, and the powerful winds and jets that erupt from this process do not simply vanish into the void. They blast outward, enriching the galactic centre with these new elements. The jet, that pillar of destructive energy, ploughs into the interstellar medium, the thin soup of gas and dust that lies between the stars. It can shock this gas, compressing it, creating pockets of high density that can then begin to collapse under their own gravity. The death of one star in the most violent way imaginable can thus trigger the birth of a new generation of stars. The very atoms that once made up a sun-like star are scattered like seeds on the galactic wind, becoming part of the raw material for future solar systems, future planets, and perhaps somewhere in the distant future life. This is the great paradoxical truth that TDs have unveiled. The black hole is both a tomb and a womb. It is an agent of creation intricately woven into the life cycle of its host galaxy. It is not merely a passive anchor, but an active gardener periodically and violently tilling the galactic soil. This duality, this constant interplay of destruction and creation, is a theme we see repeated across the cosmos, from supernovae to galaxy collisions. But nowhere is it more stark, more immediate, or more profoundly illuminating than in the death of a star at the hands of a supermassive black hole. And so we stand at the precipice of an even greater age of discovery. Our journey is far from over. What we have seen, so far as breathtaking as it has been, is merely the prologue. We have been like cartographers of a new world, sketching the coastlines with the first crude instruments. Now we are preparing to explore the interior. A new generation of sentinels is turning its eyes to the sky. The Vera C. Rubin Observatory from its perch in the Andes will soon begin a survey of unprecedented scale, scanning the entire visible sky every few nights. It will not find dozens of TDEs, it is expected to find thousands. It will catch them at the very moment of their birth, creating a vast statistical census of this cosmic violence. We will no longer be studying isolated anecdotal cases. We will have a demographic survey allowing us to understand how often this happens, what kinds of stars are most vulnerable, and what kinds of black holes are the hungriest. The Nancy Grace Roman Space Telescope, with its wide infrared gaze, will peer through the dusty veils that obscure the hearts of many galaxies, uncovering a hidden population of TDs that are currently invisible to us. These new eyes will work in concert, a global network of observatories on the ground and in space, poised to react in an instant to capture every photon, every scrap of information from the moment a TDE is born to the moment it fades from view. But the true revolution, the next great leap in our understanding, may not come from light at all. We are entering the era of multi-messenger astronomy. We are learning to perceive the universe not just with our eyes, but with new, fundamentally different senses. The same event that produces the brilliant flare of a TDE, the catastrophic stretching and shredding of a star, should also produce a cascade of other invisible signals. As the star is pulled apart, its matter accelerating and contorting under the black hole's immense gravity, it should send ripples through the very fabric of space-time. Gravitational waves. These are not whispers of light. They are the ringing of space itself, a vibration of the cosmic drumhead. Our current gravitational wave observatories like LIGO and Virgo are tuned to the high-frequency chirps of colliding black holes of stellar mass. But future space-based observatories like LISA, the Laser Interferometer Space Antenna, will be designed to listen for the deep low-frequency hum of supermassive black holes in action. A TDE captured by LISA would be a scientific treasure beyond measure. The gravitational wave signal would give us a direct, unobstructed view of the event's central engine. We could measure the black hole's mass and spin with exquisite precision. We could watch the star's orbit decay in real time. We could test the predictions of general relativity in the most extreme environment imaginable, an environment where Einstein's equations are pushed to their absolute limit. Combining that gravitational wave siren with the symphony of light from our telescopes would give us a complete 360-degree picture of the event. It would be like not only seeing the lightning strike, but also hearing the thunder and feeling the tremor in the ground beneath our feet. And there may be other messengers. The powerful jets launched by some TDEs acting as colossal particle accelerators could produce a beam of high-energy neutrinos. These ghostly particles, which barely interact with matter, would travel in a straight line from the heart of the cataclysm to us carrying information directly from the jet's launching point. Detecting neutrinos from a TDE in conjunction with light and gravitational waves would be the final piece of the puzzle. It would be the dawn of a new kind of astronomy, one that fulfills a century-old dream. We look to this future with a sense of profound anticipation, and also a sense of humility. We have come so far from abstract thought to concrete observation. We have unveiled a universe that is more violent, more dynamic, and more beautifully interconnected than we ever had the right to imagine. We have learned that the silent darkness at the heart of a galaxy is not empty but filled with a terrible potential. We have seen that the death of a star is not a finality, but a spectacular act of cosmic renewal. The universe is constantly speaking to us in a language of light, of gravity, of fundamental particles. The stories it tells are of life and death on the grandest of scales, and for the first time in the long history of our world, for the first time in the 4 billion-year story of life on Earth, we are finally learning how to listen. The stellar screams will continue to echo across the void, and our quest to understand them has only just begun.